Bismillahirrahmanirrahim. In the previous lecture, we talk about the cell, a typical cell, and then we came to this topic. That was a galvanic cell is basically a cell in which a spontaneous reaction occur to generate electricity. Is called a galvanic cell, and the batteries are the typical example of these cells. While a cell consists, this non-spontaneous reaction occur by putting electricity into the cell is called electrolytic cell. The potential difference is measured by voltmeter in a cell, and the net potential of a cell it's basically the net potential is basically the difference of the two half cell, and it's usually from anode. From cathode, the anode is deducted when the potential of anode is deducted, uh, and it's this potential is equal to EMF. Then we should come to another topic that you will see different books. That it's time consuming and space and also occupies space when you write a complete reaction of a cell. So there's a shorthand developed by scientists to write the composition or reaction of a cell. And for example, here I will see the half cell of a silver chloride cell. The half cell silver chloride is composed of silver chloride and equals phase of silver ion. It can be written here. It's like that. You should write it. You will start from the one electrode, and then you should go to the equal space. Here you can see, let me choose the highlighter, then it's easy you will find. It's a silver electrode in the solid phase. It's separated by a vertical line. This represents the phase separation boundary. This vertical line is electrolyte silver. It's a ion of silver. You can see in the aqueous phase with concentration is written as in parentheses. I will show you another example of that here a complete cell. You can see the zinc electrode. Here it is written. Uh, and it's the solid phase representation, and it's the vertical line represent the solid represent. And then here you can move from electrode to further solution form. In solution you will see the zinc, and it's another concentration and represented. It's the half cell finished. This boundary represent the junction potential or salt spread, and this is a two vertical line. Kindly note this, it's two vertical line, that's half cell finish and it's half cell started here. Now from the it's a continue event, it shows the continuity of event. Here you can see we started from electrode, then we come to the solution phase, and then we come to the salt bridge. From salt bridge you enter to another half cell, and this half cell consists of the copper ion, and this concentration representation here you can see is liquid phase from where you enter to another phase. So it's a line separation to another electrode. It's a copper, this is a solid in state. Here you can see. So the different phases, if you are facing different phases in a cell, then you should draw another separate line, and even you can write for different if it's solid, liquid, how many phases. Then you should, according to the phase, you can draw the line. Uh, I will tell you another method. Is here we can see two type of we can denote it by two methods, and the one you already mentioned, and it's another one here that instead of writing the ion, you can write the salt and representing by aqua because it's a solution form. Here the same, you have started from zinc, it's an electrode, then you should separate it by a line, and then you enter to the equal space where you can see the salt, and then it's a salt bridge represented by a double vertical line. Then you are coming here to another the salt, and it's the electrode. I will tell you that conventionally we usually write a node at the left and the left on left side. So the electrode should be on left side and it's going toward cathode toward the right side. All the events should be in sequence. This is the representation of reaction within a cell or of cell. You can write like as we already mentioned. Now we should. There's another important topic of this reference electrode. As we already mentioned here, we already mentioned that for a half cell, for a potential of a half cell can be determined in comparison to another half cell. For that, we must have an half cell of our electrode of a known a voltage or a constant. You can fix voltage or stable voltage. We should have a reference electrode, and it's the half cell for which we want to determine the potential. We connect that cell to another electrode of a stable potential, and that stable potential electrode is name is a reference electrode. Let me check the voice, then I come again to the topic. Is it working or not? Using the phone. Okay, I hope it's working. So, as I already discussed, it's and for a half cell to be the voltage of it to be determined. It is compared with a stable potential electrode, and it's called as reference electrode. As a principle, every metal ion with a half cell, every metal ion half cell can be used as stable under controlled condition as a reference electrode, but in reality it is difficult and it's not possible. It's because there are several you can say weaknesses are associated with different metals. For example, sodium and potassium metal are very reactive metals that react with electrolyte and this will be unstable in the potential of that type of electrode that contains sodium or potassium, and you use it as a reference electrode. It will not give you a stable potential. Similarly, if you are using iron, so obtaining iron in pure form is difficult to obtain iron in pure form. Some metals in ionic form, when you expose it to heat or air, they they are not stable in that form. That's why the concentration and for some metals the concentration of electrolyte control is difficult. That's why only few electrodes exist are that are existing and that are used as a reference electrode. There's some qualities for an ideal reference electrode. The one, it should have fixed potential or temperature and time. For longer time, the stability, it should be stable for longer time, even, and it should follow Nernst equation. There are three reference electrodes that are nearly ideal. It's one is saturated calomel electrode, silver electrode, and standard hydrogen electrode. Saturated calomel electrode. Typical electrode of saturated calomel electrode is consists of metallic mercury with a saturated solution of mercurous chloride, also called calomel, and it's connected with for external circuit with platinum wire so that it can conduct electron, and the mercurous ion concentration is controlled by the presence of saturated potassium chloride. The mercurous chloride solution are kept in contact with potassium chloride solution in order to control the mercurous ion concentration. The saturated name is used because of the presence of saturated solution of potassium chloride. Half cell for Kennemal electrode is written here. You can see it's mercuric chloride and then it's two electron of gain is give us two chloride ion. The net potential is 0.26 volt. It's a typical example of it's the figure of the uh, caramel electrode. You can see it's a electrode made of mercury paste and it's a porous layer. It's connected with the solution, mercurous chloride or potassium chloride, and here it's connected with platinum wire. You can connect here to another electrode by this porous plug. The basic advantage of this super cell its conductive electrode is that even evaporating small amount of liquid, still the ion concentration does not change. And you should not think the saturated term is used because of the presence of potassium chloride concentration, not because of the mercurous chloride. Another electrode, silver chloride electrode. Here is the typical electrode. It consists of a metal of silver pasted by a silver chloride and it's immersed in solution of potassium chloride and silver chloride. The half reaction of the cell is a silver chloride scain of electron as a result of the formation of AgA plus loss of electron. Net voltage is 0.22 volt. The principle similar to that of calomel electrode. However, the concentration vary. You can use it even. The concentration of potassium chloride may be 4.5, or that the voltage is 0.19825. Even if the concentration is maybe use 3.5 molar, and then the voltage is here. You can see, and uh, okay. Standard hydrogen electrode. It's another electrode, standard hydrogen electrode. Standard hydrogen electrodes, it was decided to use an electrode that should have zero value or 0 volt at all temperature. So an electrode consists of platinum, it's a platinized electrode of consists of in solution is acid, hydrogen chloride, and the electrode is connected by platinum. And its standard condition of 1 atmospheric pressure and 1 molar concentration of HCl at 25 degrees centigrade, the reduction potential is equal to 0. This is the standard condition for SHE. The net reaction or the reaction of the cell is 2 hydrogen, its gain of 2 electron is the formation of gas and its net voltage is 0. It's a typical figure of the, as you can see, the platinized electrode connected by a PT wire, and here is the container for 1 molar HCl and may be connected to another half cell for determination of the standard potential is symbolized by E with superscript 0. It represents the standard state condition. It means that 1 molar concentration of the uh, for if we are talking for hydrogen, then it's Cl 1 molar, and the gas for gas, if it's hydrogen, is 1 atmosphere pressure, and it's solid liquid present at pure. E.g., for example, platinum solid, it should exist in pure form. Then it's called the standard condition for that electrode. And to determine the potential difference or potential value, the standard hydrogen electrode is connected with another half cell, and the standard reduction potential is developed or determined. For example, zinc electrode is connected with tritium. It with standard hydrogen electrode, the potential difference can be determined. Now, its equation is already discussed. We cannot draw. It's the limit. It's not in the curriculum, but you should understand it. Nernst equation tell you the interrelationship between the variables that exist or that cause that vary, and because of these variables, the potential of a cell is varied. For example, here this variable are temperature, concentration of species in solution, and number of electron transfer. And for a reaction and reactant products, you can see here is the reactant A and B, and that's the C and D as the product. The rest equation will tell you how to write this. Is the equation. The potential is equal to the potential of a cell is equal to the standard potential minus or represent the gas constant is the temperature, n is the number of electron transfer if it's periodic constant, and this is the natural log of concentration of product and divided by concentration of reactant. It will give you what is the potential of a cell if you derive it from the standard state EMF. It's determined under standard condition, and usually you can get this value from literature. So the general form of that equation is written is here. It's derived by mathematical equation calculation. You can see it's a potential and this standard potential minus 0.059 divided by the number of electron transfer during the reaction is the log of natural log. It's not the natural, it's log to the base 10 of the species, electroactive species that reduce the molarity of the reduce the molarity of the uh, oxidized species. So it's the equation. It's the end of this topic. Hopefully, we'll meet in the next lecture. Salam alaikum.